And let's continue with the additive manufacturing from another point of view. Let's welcome on stage Martin Hedges from Neotech AMT. And he will explain some of the advances in 3D printed electronics. So over to you, Martin.
Okay, thank you very much. So good afternoon to everybody. Thank you for the introduction. So I'd like to talk a little bit about 3D printed electronics from our perspective at Neotech, talk a little bit about the state of the art, what we're doing. My agenda is as follows in this limited time that we have. I have one slide on the company overview just to explain to you, if you don't know us, who we are, what we do. Very quickly explain what 3D printed electronics is, just to give a definition of that if people that don't actually know. And then to talk about sort of the advances, look at the state of the art on a lighting proof of concept that we've done, and then talk about the next steps in that, and then show some other applications in the summary. So Neotech, we're a machine tool manufacturer based in Nuremberg, southern Germany. We've been pioneering 3D printed electronics since 2009. We built our first system in 2010. We've always had the intention of going towards volume production, so not just lab work, but getting it out into the industrial use. So we have a patented system, the 45X system, that we built first in 2012 that's been used in anger in some limited ways. And we're active across a wide variety of industries, but more about that later. So our definition of what is 3D printed electronics, so basically it's the addition of printed electronics functionality in combination with classic surface mount device components onto and or into structural components to create mechatronic systems. So we're going away from the 2D planar world into 3D. And there are two basic process routes that we can go down, which I kind of show here. We have this kind of route one that we call, so we print on an existing structure that's produced by some classical manufacturing. In this case, this is an injection molding substrate. It could be a composite component. It could be a casting, forging, whatever. So you're basically manipulating the printing and the pick and place in 3D space, putting on the outside. And then the example here we have on the right-hand side, this is what we call a fully additive route. So we're building the mechanical structure, and as we go, we're putting the electronics inside, potentially, as well as outside. So this is an X-ray image. You can see quite clearly the control here is buried in the center. You see the circuitry throughout the device. So those are the two ways that we approach things. The way that we approach it, obviously, we're a machine tool manufacturer, so we're producing the machinery, and those are basically configured, as you can see in this slide here. So we start with a box. We always work with 5-axis range of motion, CNC type. You can also look at using robots and other methodologies, but we're fixed really on this 5-axis CNC motion to allow us to get that movement, that motion to manipulate things in 3D space. We have various other things in there, advanced vision system, tool calibration. Obviously, developments don't stop. We have some inline QA, which is a beta stage, test stage. So you have that basically in your box. And then, as Neil quite rightly pointed out, when you're printing electronics, 2D, 3D, no one printing process will actually do everything that you want. So we have a selection of tools. So we cover all of the non-contact, the classic printed electronic processes that Neil kind of mentioned, piezo, aerosol, inkjet, single nozzle inkjet, multi-nozzle inkjet. At the moment, no EHD. We have structural builds, so we're building also the mechanical structure. So we used mostly FFF, so thermoplastics. We're now putting in materials, dispensing and jetting thermosets, so UV and thermal curable materials. So that builds a mechanical structure, and then you might put some adhesives in to hold your S&Ds in place. So that basically gives you the structural and electrical functionality. And then you have in the system also the pre-post processing. If you've got a UV curable material, you use UV light in the system to cure it, or you use light of various types, continuous wave, laser. So to sinter, and you might do ablation, you might do some subtractive steps, and then all of this is basically then backed up by a CAD/CAM software package that allows you to program to move to the manufacturing in a simple and efficient way. So why do we want to do this? So there are various reasons, and those really depend upon the actual application, where the benefit